Welcome to this lecture series in number theory. In this lecture, we will define and discuss the very important notion of the order of an element modulo a given integer. And we need to basically know the properties of the GCD that we proved after we discussed Bézout's theorem. So here I have written Bézout's theorem, and here are some properties of GCD that we proved. I again missed the associativity property. But anyway, I do not want to put down a comprehensive list of everything that we need to know every time. Having said that, I think this is more than sufficient for today's lecture. Okay. Some problems for practice. These I think are very interesting. So this is the binomial coefficient which I have defined for convenience over here. And this is a guided exercise. You solve the first problem and learn something, and then use it in the second problem, and so on, culminating into this very difficult problem, or very difficult looking problem, which is from the Putnam exam. So it is difficult. However, if you follow this guided exercise, it is actually pretty trivial. Okay. So let's talk about order of an element, order of an integer modulo a given integer. And then we will make a formal definition. First, we will prove a theorem and then make a formal definition. So fix two integers where the second one is non-zero and assume they are relatively prime. Okay. Then we want to say that there is an integer k in this range such that this congruence holds. All right. It's a very interesting statement. One way to state this is the following, that the inverse of a modulo n is a to the k minus 1 for some k in this range. That's one way to state it. And one thing I didn't say before, I should have, the notation for inverse. So suppose you have a and n, and a and n are relatively prime, then we know that there is some u such that this congruence holds. I mean, this is everything is modulo n, right? So the u is called an inverse of a modulo n, but we know that it is unique modulo n, meaning any two inverses differ by a multiple of n. So we can call it the inverse of a modulo n. All of these things we discussed. And there is a notation for it, which is you write a and then you write minus 1 in the exponent. It doesn't, we are not trying to say 1 upon a in the usual sense, where a is an integer. We are not talking about a rational number here. This in context, in the context of congruences, this denotes the inverse of a modulo n. Anyway, I don't think I'm going to use that notation, but at some point perhaps we will. Okay, so I hope the theorem looks very interesting because it's certainly not trivial, and the proof technique is very nice. It's a very simple proof technique and very popular and very useful in number theory and combinatorics, and even in other areas of mathematics like algebra, etc. But it's not obvious why such a thing should happen. So let me give a proof. Okay. So consider the numbers a, the square of a cube, and so on, up to a to the power n, right? And we want to show that one of them is congruent to 1 modulo n. Fine, so what we do is we will record the remainders modulo n. So let's say R1 is the remainder that a to the power 1 leaves when you divide it by n. R2 is the remainder for a to the power 2, R3 for a cube, and so on. Right? So these are remainders, and hence they are in a particular range. And here is something that we have to note. It's very simple. So note that, or rather, there is nothing to note here. The first statement is that each Ri is in 0 to n minus 1, because remainders lie in this range. But the point is, what we want to say is that we can knock off this first one. We can say that no remainder is 0. Why? Because suppose, for instance, R3 was 0. If R3 were 0, then what we would have is n divides a cube, right? What does it mean to say that the remainder of a cube is 0 modulo n? It just means to say that n divides a cube. So n divides a cube, which can be written as n divides a times a square. But a and n are relatively prime. So by the dropping property, we get n divides a square. Further apply the same argument. You can write this as n divides a times a. Again use the dropping property to write n divides a. Just drop the one which is relatively prime with the divisor. So you get that n divides a, but that is not possible since a and n are relatively prime, unless n is equal to 1, in which case everything that is written over here is trivial. If n is 1, then nothing needed to be done. So I should have written that, assume that n is greater than 1, because for n equals 1, we already know. Great. So we can erase this, right? And this is important. So now what do we have? We have n numbers, but they are all of them are in this range which has size only n minus 1. So common sense tells us that 2 of them must be the same. If they were all pairwise distinct, if no 2 of these numbers were the same, there would be exactly n different numbers written over here, but we know that there are less than n numbers written over here. So 2 must be the same, and this is called the pigeonhole principle. If you have n pigeons and you want to put them in n cages, if you have n pigeons and you want to put them into n minus 1 cages, something one should not do to animals, then some 2 pigeons are forced to reside in a common cage. You cannot have them living in different cages. It's a commonsensical statement. So by the pigeonhole principle, we see that Ri must be equal to Rj for some I and j with this property, right? If you have 2 different I and j for which Ri is equal to Rj, you can assume that I is less than j and they are in this range. Great, but what does this mean? This means that a power I is congruent to a power j modulo n. And now there are 2 ways to proceed. Let me do this by a slightly inefficient way. So this implies 0 is congruent to a to the j minus a to the I, which implies 0 is congruent to a to the j minus I minus 1 times a to the I mod n. Correct? Which means n divides a to the I times a to the j minus I minus 1. Right? But now again the dropping property kicks in. You can drop this part. A is relatively prime to n, therefore any power of a is relatively prime to n. So you can drop this entire thing, or you can drop it one by one if you don't like this. Just what we did over here. So you drop a, then you are again left with the power of a. You again drop it up until the point that you cannot drop anything, meaning up until the point that you are left with 1, at which point we get that n divides a to the j minus I minus 1, and that's it. J minus I is a positive integer because j is greater than I. This is a positive integer, you call it k, and that's what is written over here. So that proves the thing. So it's a very interesting statement, and we will see the power of it. It's a very powerful statement. It's very useful. Okay, so this calls for a definition now. Once we have this theorem, we have this definition. Fix a non-zero integer and suppose a is relatively prime to it. Then the order of a modulo n is defined as the smallest positive integer k such that a to the power k is congruent to 1 modulo n. Okay. Why should such a k exist? Well, we know that there is at least one k which satisfies this congruence. So we just say that the smallest one is the order. If there is one element, one positive integer that satisfies the property, there is a smallest positive integer that satisfies that property. The well-ordering principle, if you will. Okay, so that's that. And the notation that we will use is, we will write ORD, n in the base, and a in brackets. So this will denote the order of a modulo n. And this is not a standard notation. I just cooked it up for my exposition. Okay, so we have a very nice definition on our hands, and note that if GCD of a and n is 1, then the order of a modulo n, which exists only when this happens, is at most n. So by this reasoning, we already know that the order is at most n. One can say a much better thing. This is not the most optimal statement one can make. As we go along in the course, you will see that this at most n can be improved in most cases to a sufficient degree. When n is a prime, you cannot improve it too much, but even there you can improve it. Anyway, so fine, so far, I mean, we will be convinced, or we will be happy with this for now. Let's look at some examples to get a feel for this concept. So we want to see that the order of 2 modulo 7 is 3. What do? We have 2 power 1, 2 power 2, 2 power 3, and we see that the remainder that 2 power 1 leaves when you divide it by 7 is 2. For the next one we have 4, and for the next one we have 1 as the remainder, and that's it. 2 cube is congruent to 1 modulo 7, and 3 is the smallest positive integer, which makes this true. So the order of 2 modulo 7 is 3. Clear. What about 3? The order of 3 modulo 7 is 6 is what we want to say. So we write down the powers. And let's see what are their remainders. So the first one leaves a remainder of 3, of course. The second one leaves a remainder of 2. And for the third one, you could compute this number and then take the remainder modulo 7. But this number is 3 times that number. So the remainder that this leaves modulo 7 is 3 times this number's remainder. So you don't need to compute this huge number. You can just work with the remainder that the previous one left. I hope you know this by now. Like, this should be second nature to you. So this will leave a remainder of 6. Then you will have a remainder of 6 times 3 is 18, which leaves a remainder of 4 modulo 7. Then 3 4s are 12, hence a remainder of 5. 3 5s are 15, which leaves a remainder of 1 modulo 7, and 1 is obtained at the 6th position and nowhere before. So 6 is the order of 3 modulo 7. Okay. All right. So let's proceed. Oh, okay. So here we have an important property that we definitely want to discuss. So again, a and n are relatively prime, where n is non-zero, and suppose n is a positive integer with the property that, or n, let n be some positive integer, and then we want to say that these two statements are the same. The first statement is that n satisfies this congruence, meaning a to the power n is congruent to 1 modulo n, and the other is that order of a modulo n divides n. So these two statements are the same. Okay, this is what we want to prove. Right, so the proof is very simple. 2 implies 1 is clear. Why? Because a to the power order of a modulo n, this is congruent to 1 mod n by definition of order. And since this divides n by assumption, I mean this statement is saying that this thing divides n, you can raise both sides to a suitable number so that you will see capital N in the exponent. So what I'm saying is, say d times order of a modulo n is capital N, then by the previous congruence we have just raise both sides to the power d. On the right side nothing changes. On the right side you will have 1 power d, but that will be 1, and this implies a to the power d order n, sorry, order a is congruent to 1 mod n, but this is capital N. Right, so 2 implies 1 is trivial. Let's do 1 implies 2. So for 1 implies 2, we have been given that this congruence holds, right? Let's say the order is k. This is k, and let me also denote this congruence by a star. We want to show that k divides capital N, so we will use division with remainder theorem and show that the remainder is 0. So say capital N is kq plus r, where r is in this range. Right? Division with remainder theorem ensures this, that that you can write capital N in this way. Okay, and now by our congruence. So yeah, note that since we have taken n to be a positive integer, q will not be negative. Right? So q will be non-negative, but even if q were negative, everything was fine. There is a subtle point to be made there. But for now, let's look at the proof with the observation in mind that q is non-negative. So by 1 or by star, I mean, we get a to the power kq plus r is congruent to 1 modulo n, which implies a to the power k, or yeah, let me not skip a step. So this is a to the power kq times a to the power r, congruent to 1 modulo n. But what about this thing? This can be written as a to the power k to the power q. This is congruent to 1 modulo n. Right? While we know that this is congruent to 1 modulo n by definition of order. So this thing is congruent to 1 modulo n, and hence a to the power r is congruent to 1 mod n. But now what happened? If r were positive, we would have something strictly less than k, yet positive, satisfying this congruence. And therefore k would not be the smallest positive integer, making this congruence true. Right? If this is true and r is, well, this is true, no question about that. If r is a positive integer, that would contradict the smallestness of k. Right? So therefore r is 0. And that's it, that finishes the proof. And here I want to talk about what happens if q were negative. So what I want to say is, we already know things in general. So let me make this remark over here. We know that if we have two positive numbers, let's say 2 and 3, then, and suppose you have a square is congruent to something modulo n, suppose this congruence holds, you can raise both sides to the power 3, for example, and write this, and you can further write this. What does it mean to say a to the power minus 3, for instance? What is the meaning of this? Can we talk about that? We do not mean 1 upon a cube. That is not an integer. A to the minus 3 means you first take the inverse of a modulo n. So everything is happening in context of a particular n in mind. So this is a inverse to the power 3. That's how you interpret it. Right? As we mentioned in the previous slide, I think, that a inverse denotes in this context the inverse of a modulo n, not the usual inverse in terms of 1 divided by something, not like a rational number. So if you interpret it correctly, you can raise congruences both sides to even negative powers, as long as the things in your congruence are admitting inverses. So if you have a congruent to b modulo n, and a is relatively prime to n, and then automatically b is relatively prime to n, you can raise this congruence to negative powers while understanding that what negative powers mean in this context. So even if q are negative, nothing goes wrong. Still, you should think about why nothing goes wrong. There's a small subtlety there, very small subtlety, but still. Anyway, so we have proven this, and we could have said the same thing even for any integer. We could have said that, but just to not make things very complicated, I have proven it only for positive n's. You can say the same thing for any n, as long as we understand what that means. If n is negative, we have to understand what this means, and I've explained it. Fine. Let's look at a small application of this. So, for instance, suppose n is an odd positive integer, let's say. We want to see why this is true. So, n factorial, first of all, 2 is relatively prime to n because n is odd. So 2 has some order modulo n. Whatever is that order, call it k. And as we observed in the previous page, k will be in this range. So k will divide this. Once the order of 2 modulo n divides the exponent, this congruence holds. That's it. N factorial was designed to be divided by everything between 1 and n. Right? It's like a brute force way of getting there. And that's it. So I hope you followed why this is true. And there's a very, very interesting congruence written over here. I've written it in terms of division, but it's a congruence. Quite a nice congruence. Okay. So let us finish by a very interesting puzzle. We want to show that for every positive integer n, there is another positive integer x with the following two properties. The first is that x should be divisible by n. And second, which is very interesting, which asks that the sum of digits of x in the decimal system, the usual way of writing numbers, is equal to n. So let me explain by an example what I am trying to say. Suppose n is 13, somebody has chosen n as 13. Then this number, first of all, this is divisible by 13 because this is equal to 13 times 19. And secondly, the sum of digits is 13. Right? 7 plus 4 plus 2 is 13. So when I wrote 247, I meant that it is written in decimal system. Usually when we write numbers, we don't mention it. And I didn't mention it. But what it really means is 2 times 100 plus 4 times 100, 4 times 10 plus 7. That's what this number means. Whatever. So yeah, so this is what we want to do. And as usual, you're encouraged to pause the video and try to find your own proof. And now let me try to explain. There may be many ways of doing this, but I want to illustrate the notion of order in order to solve this question. And I will solve this under this assumption. Assume 10 and n are relatively prime. I will solve under this assumption, but from here, once you do this, it's very easy to do the general thing with where you do not get to assume this. Okay, so I will solve under this assumption. Okay, fine. So since 10 and n are relatively prime, we know there exists a positive integer k such that a to the power k, sorry, not a, 10 to the power k is congruent to 1 modulo n, where we can choose k as the order of 10 modulo n, but not necessarily. We can choose any bigger k also. So here I could write, for example, k is the order of 10 modulo n. Right, and now this implies that 10 to the power r times k is congruent to 1 modulo n for all non-negative integers r. Right, we have just raised both sides to the power r. But now this sum from r going to 0 to n minus 1 of 10 to the r k, this is what? This is congruent to n mod n. We had n congruences for r is equal to 0, r is equal to 1, r is equal to 2 up to n minus 1. We just added those congruences. So on the left side we see this, on the right side we get an n because there are n ones, which means this summation is congruent to 0 mod n, which means n divides this number. But what is this number in the decimal representation? What are the decimal digits of this number? So you should think about it, but let me explain what are the decimal digits by means of a specific example. So say n were maybe, I don't know, 5 and k were, let's say, 2 maybe. Yeah, I mean, it won't fit this congruence, but just to explain what this number would be, I'm just talking about this number. So for n5 and k2, this number is twice of r. Yeah, that's what this is. But in the decimal representation, how would you write it? You would write it as the last digit would be 1, then you would put 2 zeros and then a 1, then 2 zeros and a 1, 2 zeros and a 1, and 2 zeros and a 1. Right? This is 10 to the power 0 corresponding to r is equal to 0. Then you're adding to it 10 to the power you're adding to it 10 to the power 2. So maybe I'm writing it incorrectly. That's not what you get. You get 1, then a 0, 1, then a 0, 1, then a 0, 1, then a 0, 1. Yeah. So this is 10 to the power 0. Then you're adding 10 to the power 2. You're adding 100 to it. Then you're adding 10,000 to it, which is 10 to the power 4. Then 10 to the power 6, and then 10 to the power 8. That's what you have here, right? So all I'm saying is this number has exactly n ones in its decimal representation and every other digit is 0. N ones and everything else is 0. So what is the digital sum? The digital sum is n because there are n ones and everything else is 0. Right? So all I'm saying is that if you write a number in this fashion, all you see is ones and zeros in the decimal representation. And there will be n ones if you write it this way. So I hope this is clear. Okay, and when this assumption does not hold, you can easily modify the solution. Right? You can think about it. You can write n as a product of two things, where this is relatively prime to 10 and the other stuff and whatever. So I'll make a guided exercise maybe in the next lecture to address the other case or the remaining part of this proof. All right, but this is the main idea. As usual, like, comment, share, subscribe, and I will see you next time.